Okay, real quick, let me just tell you, what if you have improper fractions? Or what if the degree of the numerator is larger than the degree of the denominator? Well, in that case, you can do long division. Now, I'm going to assume that you know how to do long division, so I've given you my long division over here. You can pause the video and look at it here. But you can see that I can take this fraction here and I can use long division, and I can actually rewrite that as x minus 1 plus the fraction x plus 1 over x squared plus 2x plus 2. So in other words, I can break this integral up into two integrals. Now, we know how to integrate x minus 1. To integrate x minus 1, you just integrate the x and you get x squared over 2. Integrate the minus 1, you get minus x. Okay, but this right here, you would want to let u, if you let u equal x squared plus 2x, then du would be 2x plus 2, which is actually twice as much as what we have here. So what you would do here is you would have to multiply the inside by 2 and then the outside by half, and then that would give you, then you would have du in the numerator and u in the denominator. And so that's where I got this, the 1/2 du over u, and that's where u equals the x squared plus 2x plus 2. So if you integrate the du over u integral, you just get a natural log of the absolute value u, and remember u is the quadratic x squared plus 2x plus 2. And then I had a 1/2, so that's where the 1/2 came from. The 1/2 was outside the integral. And then of course I also brought over these terms that I had already integrated. So I have x squared over 2 minus x plus 1/2 times the natural log of this absolute value plus a constant. And there's a practice problem there. If you want to do that one, you can do that one. And again, just do what I did in that previous problem. Do long division and then rewrite the integral as the sum of the two integrals that contain your quotient and your remainder term. Okay, and then you can integrate each of those separately. Okay, all right, so now back to this decomposition. So here we're going to have quadratic factors that are irreducible. So let's take a look at what we have here. Here the degree of the numerator is not greater than the degree of the denominator, so we can go back to this decomposition method. But here's what we have to do here. If you look at the denominator here, you actually can factor out an x squared out of this, and when you factor out an x squared out of this, your denominator gives you an x squared and an x squared plus 1. So these are actually both quadratic factors. And so we have a quadratic factor here, and we have a quadratic factor here. So what I'm going to do here with quadratic factors, if you go back and look at the rule, with the quadratic factors, when you break this up, you don't have just constants in the numerator, you actually have a linear expression. So here I would have a constant times x plus another constant for the x squared denominator. And then for the x squared plus 1 denominator, I would have another constant times x plus a constant. So that's how you deal with it when you have quadratic factors. Now, these quadratic factors aren't repeated, because to be repeated, I would have to have x squared plus 1 to some power. So we'll do a repeated one later. Now, if I eliminate the denominators, I can eliminate the denominators. I would just multiply everything by the product. Well, I'd basically just multiply everything by this, which is the LCD. So if I multiply the left side by that, then the denominators will just cancel, and I'll just get this polynomial. And if I multiply each of these terms by the LCD, then I'll just get ax plus b. So I'll get ax plus b times x squared plus 1, because the x squareds would have canceled here. And then when I multiply this LCD by the second term, I get cx plus d times x squared, because the x squared plus 1s were to cancel. Now, I can FOIL this, so just FOIL this and you'll get ax cubed plus ax plus bx squared plus b. And then here you can distribute and you'll get cx cubed plus dx squared. Now let's get your terms together. So I have ax cubed here and cx cubed here. So I'm kind of doing this in my head. So if I factor the x cubed out of those two, that would give me a plus c x cubed. And then here I have bx squared here, and I have dx squared here. So if I factor the x squared out of those two terms, I have b plus d x squared. So the coefficient of x squared is b plus d. And then I only have one x term, and that's the ax, and I only have one constant term, and that's the b. Okay, so now if you equate these, you can see here that the coefficient of the cubed term is 5, so that means a plus c must equal 5. The coefficient of the squared term is minus 3, so b plus d must equal minus 3. And then the coefficient of the x term is 2, so a must be 2, so that's good because now we know what a is. And the constant term is negative 1, so b must be negative 1. So we know what a and b are, and since you know a is 2, let's see, okay, so since a equal 2, we can say 2 plus what equal 5, so that means c would be 3. And since b equals negative 1, we can go to the second one and say, all right, negative 1 plus what is negative 3, and then then we can solve that for d. D would be negative 2. So now that we have all four of these values, a, b, c, and d, then we can go back up here and plug them in. So we know that since a is 2 and b is negative 1, this numerator must be 2x minus 1, and then of course it's going to be over the denominator, x squared. And then this right here, c is 3 and d is minus 2, so we'd have 3x minus 2 over x squared plus 1. Now I want to do one more thing. I can actually rewrite this as 2x over x squared, and 2x over x squared is 2 over x, minus 1 over x squared. So I can actually break that first one up into those two terms. And then I can take this and break it up into two terms. It'd be 3x over x squared plus 1, and then minus 2 over x squared plus 1. So eventually I can actually get this written as 4 terms. So now I can integrate each of these terms separately. So I can integrate 2 over x using my logs. I can integrate 1 over x squared dx using the power rule. And then I can actually integrate this one using a u substitution and logs. And this one actually is an arctan. So you might want to research that one. You're going to have to use the arctan function on that one. But so this one you're going to have, if you go back and look at the arctan, you'll find that if you integrate 1 over x squared plus 1, it's actually arctan of x. And since we have a 2 in the denominator, in the numerator, then that's going to be 2 times the arctan of x. And of course there's a minus in front of the integral, so it's minus 2 arctan of x plus c. But anyway, the point is once you get it into these 4 terms, you can just integrate these terms individually, and then you'll get the result for the original fraction. Okay? And then here's another practice example that you can do similar to this. And so go ahead and pause the video if you need to and practice on that next problem. The answer is given. Okay, now if you have repeated irreducible quadratic factors, like here I have x squared plus 1 quantity squared, well then I'm going to have a linear term for x squared plus 1, and I've got to have a linear term for x squared plus 1 quantity squared. So each one you're going to have, I'm using A1 and B1 here. You could just use AX plus B and CX plus D if you want to, but I'm saying A1X plus B1 over X squared plus 1, and then A2X plus B2 over X squared plus 1 squared. So it's kind of like what we did earlier with the repeated factors, but this time I have, instead of repeated linear factors, I have repeated quadratic factors. Now, just multiply both sides by x squared plus 1 quantity squared. Okay, that's all you have to do. So multiply each term by x squared plus 1 quantity squared, and then on the left you'll just get that polynomial. On the right you'll get the numerator times x squared plus 1, and then the second term you'll just get the numerator because the x squared plus 1 over squared canceled with the x squared plus 1 squared in the denominator. Now go ahead and FOIL this, okay, and then you'll get a1x cubed plus a1x plus b1x squared plus b1, bring down the a2x plus b2. Now if you look at, you've got only one cubed term, and that's the a1x cubed, and then you've only got one squared term, and that's the b1x squared. And then the x terms, you've got an a1x and an a2x, so if you factor out the x, that'll give you a1 plus a2x. And then you've got two constant terms, b1 and b2. So now comparing it with the left side, a1 has to equal the 5 because the coefficients of the cube terms must be the same, and the b1 must equal the -3 because those terms have to be the same. And then we know a1 plus a2 must equal the coefficient of the x term, which is 7, and then b1 plus b2 must equal the constant term, which is -3. Well, then finally, if you know a1 plus a2 has to be 7, you know a1 is 5, then you know a2 is 2. And if you know that b1 plus b2 is -3, and you know b1 is -3, then you know b2 is 0. So now, if I rewrite it like this up here, that would give me two integrals. So the first integral, since a1 is 5 and b1 is -3, that'd give me 5x minus 3 over x squared plus 1 dx. And then here, since a2 is 2 and b2 is 0, then I would just get 2x over x squared plus 1 quantity squared. Now this one I can break up into two more integrals, so I can write this as the integral of 5x over x squared plus 1 dx, and then minus the integral of 3 over x squared plus 1 dx, and I just put the 3 out here, and then plus this other integral on the right. Now I'll leave you to evaluate those integrals by now, but that's what you would do. You would go ahead and evaluate those integrals. Okay, this one has a linear factor and a quadratic factor. So for the linear factor that occurs once, you'd have a over x. For the quadratic factor that occurs twice, you'd have bx plus c over x squared plus 1, and then you could do dx plus c over x squared plus 1 quantity squared. Now all I have to do is eliminate the denominators and then collect the like terms, so you can freeze this and work your way through it if you want to. But you collect your like terms. But here's what's interesting here. On the left side, when I eliminate the denominators, all I get is the 1. So I know a is 1, and then when I combine the terms here, I know that all these other coefficients are 0. So a plus b must be 0, c must be 0, 2a plus b plus d must be 0, and c plus e must be 0. But with a little effort, you can find out, since you know a is 1, you can find these other values, and then you can rewrite this fraction up here. Now that you know a, b, c, d, and e, you can rewrite this fraction, and then I'll leave you to evaluate those integrals there. Okay, that's pretty much finishes the partial fraction decomposition section. I do have one more section I'll cover that shows you a little bit different technique that can be used on certain problems in order to solve for those constants.